Section 10.2, we're going to find arc measures and learn about arc measures. So we're going to name some minor and major arcs and find measures of arcs and central angles. So let's start with some vocabulary. First of all, a central angle is an angle whose vertex is the center of the circle. So for example, ACB is a central angle. A minor arc is an arc that is formed by a central angle whose measure is less than 180 degrees. So this right here is a minor arc, because this degree measure right in here is less than 180. And an arc is just part of a circle. It's part of the curved part of the circle. So arcs in general are part of the circle. So we have minor arcs that are less than 180 degrees, and we have major arcs that are formed by a central angle whose measure is greater than 180 degrees. So our minor arc here is AB, and our major arc here is ADB. So ADB. A semicircle is an arc with endpoints of a diameter, with endpoints that are the endpoints are the diameter. So semicircle, an arc with endpoints that are the endpoints of a diameter. So if we had a diameter that went all the way through like this, then arc like A, probably need another letter in here. So arc AED is a semicircle if AD is a diameter. I've already kind of written some arcs, but when we name arcs, we use that little symbol. It's like a little curve symbol. So this is our symbol for arc. And minor arcs are named by their endpoints with 2 letters, and major arcs are named by, and semicircles are named by their endpoints and a point on the arc. So we always use 3 letters, and that's how we can determine which arc they're referencing. Because if they just use 2 letters, we might be considering going from the right to the left or left to the right, and you would have different sizes of those arcs. So let's see if we can give some examples of these. Some are kind of following up from yesterday. But a chord, what would be an example of a chord? Well, all you need for a chord is the endpoints to be on the circle itself. So we could say that FE is a chord, or AB is a chord. A radius is from the center to an endpoint. So we could say like AC is a radius, or you could say CD. A diameter goes through the center, so again, we could have AB being a diameter, or we could have EF being a diameter, or FE. So what would be a minor arc? Well, there's several of them. Here is a minor arc, so we would call that AD, that's a minor arc. Or you could have DE. And so we name it with those 2 letters because they are minor arcs. A major arc would be greater than that. So if we look at this arc from A through all the way around to F, that is a major arc. So we could name that major arc ADF. So that is the arc that's going all the way. Okay, there's several of them in here, but that would be one example. Another example would be arc DEF. A semicircle, remember, you have a diameter and a semicircle endpoints are the diameter, the endpoints of the arc. So an example of a semicircle could be, if we use FE as our diameter, we could use arc FBE. Or another one could be arc ADB. And a central angle is any angle whose vertex is in the center. So if we look at ACD, angle ACD is a central angle. Or we could use angle FCD. There's many central angles in here as well, but there's a couple examples for you. Okay, so let's talk about the measure of arcs. So we actually can talk about arcs as like part of the circumference, but we can also talk about it in terms of it being a measure. So if we think about this for just a minute, if we think about going all the way around the circle, that's 360 degrees. And it's 360 degrees whether you're going around the outside of the circle, or if you're going around the inside of the circle, you still have 360 degrees. So when we measure, the measure of a minor arc is really just the measure of its central angle. So if that central angle is 50 degrees, then that arc measure is also 50 degrees. The measure of a major arc is the difference between 360 and the measure of the related minor arc. So if we were trying to find the measure of the major arc, which let's say we want to find ADB, then we're just going to take 360 and subtract the 50 to get 310 degrees. And the measure of a semicircle is always 180 degrees. So that's how we measure arcs. So there's a postulate that goes with this, and it talks about adjacent arcs. And just like adjacent angles share a common side, adjacent arcs are adjacent if they have a common endpoint. And if that's true, you can add the measures of the two adjacent arcs. So if we take a look at arc AB and we take a look at arc CB, those are adjacent arcs. So arc AB and BC are adjacent. Well, if you look at AB and you look at BC, if you add them together, you actually get the entire major arc ABC. So if we wanted to know what the measure of this whole arc would be, we'd simply add the two pieces, and that is the arc addition postulate. The measure of an arc formed by two adjacent arcs is the sum of the measures of those two arcs. So it's just like angle addition and segment addition. We also have arc addition, and that makes sense, hopefully. All right, so in circle O, NR and MQ are diameters. Okay, so NR right here is a diameter, and MQ is a diameter. Find the following arc measures. So we want to find the arc measure MR. So this arc measure is one of them we want to find. Well, we're given that this is 70, so we know that this is 70 degrees. We know that this is 30 inside here, and that's a diameter, so the total between 70, 30, and NOP, they all have to add up to 180 degrees, all those degree measures, so that makes this piece right in here 80 degrees. So that makes this arc also 80 degrees. So that measure of this arc right in here, that central angle, is 80 degrees. So how does that help us? Well, then we also know, since this right here is also diameter, then we know 70 plus this angle right here also has to be 180, so that makes that 110 degrees. So that makes MR, this arc right here, 110 degrees. Now, that might not have been the simplest way to go about it, but I think we've got a lot of information that we can use to find the rest of these now. So now we want to find arc MPR. So it's good to like highlight sometimes. You're going from M around through P and then over to R. Well, notice that is just the major arc with the same endpoints as the minor arc. So all I have to do is take 360 and subtract the 110 reference minor arc, and I get 250 degrees. Okay, so now let's find RQ. So again, I'll reference RQ. So RQ is this arc now. Well, that's the same as its central angle, so that will be 70 degrees. And NMR. So from N through M all the way over to R, well, that's 180 degrees because its endpoints are that diameter, so 180 degrees. And last but not least, PRN. So let's take a look at P around to R and over to, way over to N. So now these are my endpoints, and it is the same endpoints as the central angle, 80 degrees. So now I would just take 360, subtract the 80, or you could use arc addition here and get 280 degrees. So now let's talk about congruent circles. Two circles that have the same radius are called congruent circles. Congruent arcs are two arcs that have the same measure, and they have to be arcs of the same circle or congruent circles. So, can we tell whether arc AB is congruent to CD? Explain. Well, if you look at this first example, okay, you go, oh, well, they're congruent because this is 65, okay, and so this has to be 65, each of these, but those are not congruent arcs because the arcs are not congruent because they're not in the same circle, or they're not in congruent circles. In other words, we don't know if this radius and this radius are the same. So the arcs are not congruent, or we at least do not know that because we do not have congruent circles. And maybe a picture that kind of shows this is if I go ahead and draw another circle in here, okay, and this is still the same degree measure for both of those, but you can see right here, well, actually, yeah, that's what it would mean to be in congruent circles. Sorry. But this doesn't necessarily have to be true. So that's what it would look like if they were in congruent circles. What about the second example? Well, now we can see the radii are marked congruent right here and right here. So that's how you know that those are congruent circles. So that means the arcs are also congruent. So yes, because we do have congruent circles. And you know that because radii, that's the plural of radius, radii are congruent. You can tell that by the way it's marked. So that can be kind of tricky sometimes. All right, one last example, just kind of using these ideas here. This is using a clock. And many of you don't use a clock anymore. It's all digital. But in the clock face shown at the right, the positions of the numbers determine congruent arcs along the circle. So this arc right here is congruent to this arc right here, etc. They're all congruent. So what is the measure of the arc between any two consecutive numbers? So we want to know, what is this? Well, if you take 360 degrees and you divide it by the number of arcs, and how many arcs do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 congruent arcs, so I just take 360 divided by 12, and it's going to be 30 degrees between any two numbers. So an arc is traced out by the end of the second hand as it moves from 12 to 4. So if this arc moves from 12 over to 4, is that a major arc or a minor arc? Well, it's a minor arc because it's less than 180 degrees. So what about starting at the 2? What number does the end of the second, starting at 2, what number does the end of the second hand reach as it completes a semicircle? So if we start at the 2, and we're going to complete a semicircle, which would be over here, it would be going through 6 arcs, and that would end at 8. When the second hand moves from the 8 to the 3, what is the measure of the arc? Okay, so let's paste that out. If it goes from the 8 and it goes around to the 3, it's 30 degrees past 180, so it would be